was just exploring the idea that you have these two the same. You have these two ways of doing this. One is you have the same set of cells have two phases, or you have the same set of sort of mini columns where you then in one layer it's dense and the next layer is sparse. Those are the.
Are we on some level assuming that the cylinder? So I see that the cylinder has overlap with can and have overlap with.
There's no overlap. This is the same, but these two are different.
Yeah, but in terms of the actual populations, does a cylinder has overlap with can?
In both these examples.
So we want to drop.
Well, in this example where you're doing it on different phases, these are the exact same cells. In this example, based on the tank paper, they're the exact same mini columns or grid cells. Imagine a grid cell has both. Imagine you have the classic grid cell and below it there's a bunch of other cells. What do you call them, mini columns? So the path integration works on the set of them. But they're actually physically different cells. So yeah, they're physically different cells. Does that make sense? In one case, you're going to look at it in one part of the phase, and the other part of the phase will have a completely different representation. Here, you look at one set of cells, now you look at the other cells underneath it, it's a different representation. Although there are commonalities between them, but you're not going to see. I guess they're in some sense they're overlapping populations, right? The sparse one is a subset of the. In this case, the sparse pattern is a subset of the non-sparse pattern. In this case, the sparse pattern is not it's a different set of cells exactly, completely.
Yeah, because if we're assuming that we're dropping cells from representation to be more specific, then they have to be subset.
No, it's more like you have a dense. Imagine we're looking down on the tank paper. You're looking down at these cells, and they're acting like grid cells. And then the question is, below them in the column, there's another set of cells that are co-aligned with these, but they're sparser. So like when you do path integration, what you need to have happen here is that path integration has to work on the set of these, like a little mini column. So the mini column is path integrated, but then we pick a subset of them. That's totally possible, by the way. The mini columns could be path integrated. So I don't see a problem with that. So you path integrate the whole set, but then this is a difference. This is not the same cell as this one, but when this one is active, this one's always going to be active. When this one's active, only some of these, one or fewer of these are going to be active.
Okay.
Something like that. So these aren't exactly the same, these two scenarios. Because this is literally the same set of cells at different phases. It's literally a different set of cells. But if you think about their vertical co-alignment, they're overlapping. How's that?
Yeah.
I'm just trying to figure what would the implications of these two ideas be. What would allow us to do classification? Would it allow us to do I suppose if I a lot of ideas running through my head. What are the problems? We want to let's say we want to be able to we don't want to have to relearn points on common objects. Does it solve that problem? So let's say I start by learning I'm struggling, like, why would I start a new object? Well, why would I pick a cylinder versus something other shape? I mean, clearly here, if I do the prediction based on these guys, it's got, any prediction based on the cylinder would be common between the can and the coffee cup, right? It's the, but sometimes I want to make a prediction about this, which is, unique, which is a handle. But how would I only know to do that then? I mean, like, I'm moving my finger around, I have a unique representation down here, and I have a less unique representation up here. Why wouldn't I learn every feature on the cylinder using this representation? Why would I say, oh no, only on the smooth parts, the common parts, so I gotta use this one? And how do I know when to make a prediction based on this one? What I'm saying about that?
Yeah.
Here's an idea. What if we assumed it was this one? This method, you go through phases. So you're gonna have, at one moment in time, you're gonna have the cylinder. And then the next moment in time, you have can, then you have the cylinder. And then you have the can, every phase. If this prediction is correct prediction, then I just ignore this. I don't want to learn anything here. It's like, there's nothing, don't learn a unique thing for the can because it's correct for the cylinder. But if this is not correct, then you want to learn this one. You say, hey, that's not a regular cylinder, that's something unique. I'll form the representation. I'll use the representation for the I guess it was coffee cup. I guess it should have been right. I'm gonna use the representation for the cup. I found that there's a feature there that says, oh, that's to be the cup. So as I go through learning, I go, okay, similarly, I've learned a cylinder already. I don't know how that happened, but I learned a cylinder already. I'm going around and I say, okay, here's what the cylinder feels like. And now I'm going to present a new object. I come along and it's incorrect prediction, but I already felt up on the cylinder. So, well, it must be a variation of the cylinder. So I'm going to learn that on the cylinder, there's a unique representation for this. I've had that unique representation. Oh, here it is. I've had that unique representation all along. Right? Yeah, cup and cup. But I just ignore it here and I pay attention. I ignore that here, but I pay attention to here. So now I'm going on and predicting cylinder, but I'm going cylinder, cup, making my predictions on the cylinder, but then I get to the cup, I say, yeah, in this case, I have a prediction unique for the cup. Therefore, this is a cylinder with a handle on it.
So we always learn on the generic one until the generic one does not become plausible.
Right. The general idea, I'm just beginning, is like, yeah, I'll stick with the denser one that's, at least I'm trying to solve this problem. I don't want to relearn all the common points on objects, right? So as soon as I know I'm on a cup versus this is a cylinder, but I could be, if I knew I was on a can, I'd make a different prediction. So my point is, as soon as I lock onto something, like, oh, it's a can versus a cup versus a, football, whatever. I have this alternate representation is unique.
That's only speaking, learning a morphological model, or because like the cylinder can be like different colors as well, or like even if you're on the main part of the cup, you would still make different predictions, like depending which cup it is for color that's being sensed there, for example.
You're getting ahead of where I am. I'm just thinking just mechanism, because I have a mechanism that represents a base object and a non-base object. I'm not thinking even anything beyond that at this point in time. Would it not work? Are you thinking of examples that wouldn't work, or you?
No, I'm just thinking it will be a bit more involved once we take into account features like color.
Well, I don't know. Basically, I'm alternating between a generic SDR and a specific SDR, a generic SDR and a specific SDR. And I could, with the specific SDR, I can associate with anything, color, it's just I can just associate whatever the input is at that time with this specific SPR. So I don't think why it would be different with color or anything else. It's just like, which kind of location am I representing it as? Am I using the generic one or the specific one?
Yeah, I just mean, then we would basically never use the generic one.
Why? We use it anytime we don't have a specific prediction.
Yeah, well. To predict the morphology.
Well, I'm not even stuck on morphology. I'm just saying I'm alternating representations here. All I'm saying is I have a generic something representation, and if I've learned that and now I have something which is incorrect prediction, then I will switch to the specific version of it to make that prediction for the specific version.
Yeah, the only, like, when I think of it through it practically, I'm just thinking like the prediction will almost always be off in some features for the cylinder. Like if we're on a can, we will feel like we will sense like the redness of the can that might not be in the generic model, and we will sense like this riffled structure of the can that you usually have, like the little wavy structure.
So what's
And
wrong
stuff
with,
like-
what's wrong with learning that?
Nothing's wrong with learning that. I'm just saying like it will be rare that it actually matches the generic model exactly.
Does it have to? So the
You're saying
generic-
a generic model might be purely morphology. Yeah.
It might just be very rough morphology.
Okay. I like that actually, because otherwise it wouldn't be very generic, would it?
Yeah, no. It would be like, I really like this idea, and I think it's nice because like everything can be kind of decomposed into these basic object shapes. Like if you go into like drawing books and stuff, they compose the scene into cylinders and circles and stuff like that.
Yeah.
But it just seems like if you're oscillating like this, and once we take all of the different features into account, it feels like we almost never will make a accurate prediction with the generic model for what we're actually sensing.
What if we said, what if we say this one is only morphology,
Yeah,
right? That's where you're going,
yeah,
right? It's only morphology. So somehow we're able to learn this without paying attention to the features.
yeah,
features.
that's what.
And then that means they're not connected the same. That would mean like,
Yeah, it's really more like, are you thinking of this being happening with the grid cells or in layer 2, 3
I
right
don't
now?
know, I'm really confused
Okay.
at this point.
Because yeah, when we were talking about it being in layer, like with the grid cell idea, that made a lot of sense to me, because that way we only have morphology in that generic model, and it just tells us like how we path integrate along that 3-dimensional shape.
So let's review, let's take a look at layer 4 here. Layer 4 is composed of mini columns. And those mini columns have they represent the same orientation of a feature, right? That's all they represent. And those mini columns are, I believe, are defined by these bipolar cells, which are a separate set of cells that these guys then connect vertically across all these. So what the spatial pooling occurs on these guys. It doesn't occur on these cells, it occurs here. This is like this is a set of cells, each one represents a minicolumn. These cells exist just like this, they have little tails. And so this is where the spatial pooling occurs from. And these cells are these are big neurons with lots of synapses, and they can learn too. So if I want to just purely learn morphology, I would be trying to learn with these cells. These are like, this is an orientation at this location. That's all it represents. It's like an edge at this location in space. So these cells themselves know nothing about color or texture or any other detail. It's just, this is like pure orientation. And then these are the details of what is at that orientation at that location, right? So these cells would represent orientation plus feature plus location. Because they're getting location from down here. So if I wanted, if I let's say I had if I had I'm trying, where was my generic and my specific STR here? I was trying to imagine, I'm not sure what, let's say it was in the, let's say it's a 6A, and then let's say there's a layer of cells here, which is the classic grid cells. And then there's a layer of cells underneath it, which is more sparse. So now we're going back to this idea here. There's two things on top of each other, not in time. These grid cells could connect to these guys, where these guys would connect to these guys. Would that work? So my grid cells are pretty, they're not very super unique. But I could learn to associate, there's not, that is the way grid cells work, and they can re-anchor. There's not that many combinations because they're not sparse enough, but there's a fair number of combinations, but there's not like a million or billion or trillion or whatever. So you could say there's some number of ways that grid cells can re-anchor. It's a limited set. They may correspond to the number of ways I can represent morphology. So as I go through these locations here, I can say, oh, well, there's an object, there's an edge or something at some orientation at that location. That's all I know. And so they would be path integration with basic morphology, featureless shapes, something like that.
Yeah.
And then these cells here, these hypothetical sparser cells that I made up, they also they path integrate in the sense that the same alignment would actually, but they're sparser. And so this would be unique. This would be a unique representation of location, and that would be associated with these.
Yeah, I like that idea. Would this also, I don't know, it might be a slightly tangential question, but I remember before we talked about how we can path integrate on three-dimensional objects. Like, how do I know if I go once around the cup and back at the original location?
Yeah.
Would that kind of explain it as well? Like, we would have grid cells in layer 6A that learn specifically path integration properties, or like how you move on a cylindrical object, and then use that to communicate to upper layer 4 which orientation should be sensed next.
I don't know. That sounds complicated. I'm lost on now. I partially don't understand the question.
Oh. But basically, like, grid cells are usually explained in two-dimensional space, so like as a navigation task. But the question was basically how would they work on a three-dimensional object, like where we can move once around the object and end up in the same location.
Yeah.
And if they're, I think in the past we talked about how we might be learning grid cells for different spaces. And if we are saying now that we might be encoding like general morphology, or like what do we call it, the abstract object, then that might be how.
Right, so as a general question, how do we represent three-dimensional space versus two-dimensional space? I think we've talked about this before. I'm very confused by this. There's a lot of evidence to suggest that grid cells don't do three-dimensional space very well. And remember I gave the example of the cube with faces on the 6 faces of the cube. You kind of remember each face, but you don't remember where the faces are relative to each other. And like,
Yeah, that's,
I remember faces like this, but I can't really recreate a face like this. It's really hard to do.
yeah, that's what I'm kind of also referring to, that we might not be representing the whole 3-dimensional space and then the object within that 3D space, but instead like kind of an unrolled surface of the object, like like when you have a cube and you unroll it.
Right,
it's like
but it's funny because it's when the cube example, you don't really unroll it in the sense like, oh, I learned this and I learned this and I learned this and I learned this. It's sort of like I can't, like often if I showed you a die, if I showed you a cube with 2 pictures on the sides here, generally I can't remember which picture is relative to which picture. You know what I'm saying? I can remember this picture, I can remember this picture, but I can't say unless there was like a story that was being untold. You know what I'm saying? I might see the cube like this. And I see there's a pattern here and there's a pattern there. Maybe say there was different, not A and B, but there's some picture A and picture B. I don't actually remember this view. I never can remember this view. I can't recreate this view. I can only create the face on view. You know, like that. You can't draw this. I can't remember. I typically can't remember what's on this face versus this face. So I always wondered is like, are you actually just remembering a series of 2-dimensional patches? They somehow stitch together.
Yeah, but then you do know that if the dice gets turned around 4 times, you're back on the same.
Right, you kind of know
place.
that, right? But I don't remember the sequence of what I see as I do it.
Yeah,
That's pretty rare. I mean, obviously, if it was just a series of 4 images and nothing on the other side, you might be able to do it. Can we put that aside for the moment?
yeah, sure.
Let me just try to finish this one for the moment. Maybe you're onto something. I don't know.
Yeah, I was just thinking this might be a solution.
It
to
might
that,
be, but
but
maybe you'll have to help me understand your solution because I'm confused by it. Where are they? Where were we on this one? So you got these are these bipolar cells, and I always forget which ones they are. They're not the chandelier cells, they're I forget. And then the theory is that they drive these guys. So at this level, these cells are representing just orientation. I'm just repeating what I said earlier. This is just orientation with no features, and this would be a dense grid cell representation. And so I could re-anchor these based on the basic orientation of the room, or the orientation of the morphology of the object. Excuse me. And then we could always form a unique representation here. And you would associate that with these guys, which is also a unique representation here. I don't know how do I pick a unique how do I pick one here? I guess pick a random set here and a random set here. Imagine I'm going to draw this a little differently, just to make it look more parallel. You have this idea is you have a set of grid cells. These are classic grid cells. And then you have a set of ones underneath it. And maybe tell me a few, it doesn't have to be a lot. This is a unique location. These are sparser. Whatever, because they're picking one of many in under each grid cell. I want path integration to occur. Well, path integration could occur for these. I don't think path integration occurs for these so easily. I mean, like if I move from location to location, I'd have a different set of sparse patterns here. I don't know how I would predict the correct sparse pattern given given one location, I have a sparse pattern here. And then I move to the next location, so I know where to move up here. How do I know which sparse pattern down here to activate? I don't think I would know. I would just know it's, well, only if I learn these connections between them could I do that, but I can't really do that. So the thing I'm trying to do is I'm on an object and I move to a new location. I want to maybe be able to make a specific prediction on that new location. That means I have to path integrate and select these cells correctly. And could I have done that?
Could that be done with the layer 4 connection?
How?
If we,
If I projected back down here?
yeah,
It could, yeah, I suppose it could. So what would that tell me? I would say,
it would give you information on which object we think we're on.
then I'd have to learn, it wouldn't be path integration, but it would be like saying, oh, if I know what the feature is, then I know what my location is. I want to be in a situation where I'm at some point on an object, I move, and I want to be able to predict the next feature. So layer 4 is not active yet. So I can't rely on what's here. This will only represent the previous location. So this can't tell me what my new location is yet. It's like, I want to path integrate to the new location.
I thought that comes from the grid cells, the new location.
Right, I'm just saying, how do I path integrate the sparser version here?
Are you thinking of this as like mini columns
I
underneath
don't know,
each grid
I'm
cell?
not certain. They could be like mini columns.
Because then we could have like underneath the grid cells are doing the path integration, and then underneath each grid cell would be kind of like a mini column, and then the inhibitory connections between
Right,
L4
but how do I
and
know
6
when my mini column changes, the sparse activation of the mini column changes, how do I know which cell in the next mini column is going to become active? I can predict what next column to go to, but I don't know which cells be selected in that column I should go to.
Could this be selected by the inhibitory connections between L4 and L6?
It could be, I actually think I have an idea how to do this. Oh, wait, hang on a second. I didn't hear what you said, I'm sorry, but I think I have an idea to do this. Forget that these are mini columns. Remember that the tank paper, we had basically 6 grid cell modules. And there were like, there was a little cluster of activity in each one of them. And so the idea here is that these move around as a group, and you re-anchor, you pick a different set to move around as a group. That's what it looked like. Then I imagined there was another cell underneath each of these was an active cell below it. And that was more sparse. Imagine the whole path integration. Okay, let me rephrase it. The way I've always thought about mini columns in the past is you have sort of a random cell in each one that's active, and the next moment you have a different random cell in each one that's active, and there's no correlation to them. But what if in the case is this I had a cell here and under this cell, and I had another one here under this cell, and another one here under this cell. But path integration, but these were sort of separate little layers. And so path integration means that just like these cells all move in path integration, the next layer down would all move in path integration. And the next layer down would all move in path integration. So that the active cell moves in the same layer. It can't change to a different one here. It's not like a random choice. It's like you have a so let's say I have 6 active cells here, and underneath it, there's actually be more than 6, there's a bunch around here. let's say well, let's just say 6 for a moment, see if it works. And then underneath it, let's say I have 2 in the next layer down, and underneath that I have another 2, and the next layer down, another 2. And so there's like, imagine the layers of cells are actually really thin little layers, and that, I'm making this up, totally making this up. And so the 2 cells here move around as if, just like these do, and the 2 cells below that move around just like these do. So I'm not picking from the whole set, I'm just picking these 2 move around, these 2 move around, these 2 move around. So I have then I can do path integration, because each cell is path integrating correctly. It's not like, it's not randomly jumping up and down. I'm not picking a mini column and picking an active cell in it. It's like saying, it's like that they have to stay, that there's a path integration within its own little thin layer of cells. And I'm not just picking some random SDR out of a set of mini columns, which is what we've been doing in the past. This is interesting. I don't know if you're following this.
Yeah, I'm not sure if I followed all of
Okay,
that.
okay. Our usual way of doing it is say, here's a bunch of mini columns, pick 1 in each column randomly. That gives you a random SDR, gives you a maximum random SDR. But when it comes to, then if I learn a sequence in the temporal memory, I can learn a sequence between this random SDR and the next random SDR. That doesn't work for path integration, because I need to have a sparse representation that when I do path integration, I always get the correct next sparse. There's a determined next sparse representation. I can't just pick one randomly. It has to be determined. I have to be able to say, given a sparse representation on the cup, and I move, I know exactly what sparse representation I'm going to get next. It has to be determined in the mechanism. It can't be just learned, because I need to be able to move through the object space in the sparse representation of the object without, I have to predict what based on this, the motor input, I have to predict the next SCR location. And I can't just pick random cells to do that. I have to have a mechanism for picking the next sparse representation. So that's the problem I'm trying to solve. And I'm saying, like, even if I just had even imagine that each little layer, I don't know if this is even possible, but each layer of cells, an individual cell that's in one of these little sparse layers will be path integrated. It'll move to one of these next columns. It will move to one of these next columns based on path integration. It won't. I have to be able to predict where it's going to be. So I need to go from a sparse pattern to a sparse pattern to a sparse pattern, deterministically based on motor input. And so if I just imagine these as little slices that are sparse instead of 6, let's say there's 2 active in each little layer, then each layer path integrates, each cell moves to the next column just like these up here do, and then it's deterministic. I don't know if the numbers work out, but it would be deterministic. Let's say I had 15 layers of cells here. This is not atypical. 15 layers of cells. I have 2 active, because again, I have 6 bumps here. Let's say I have 2 active in each one. So that would be 2 to the 15th space. It's not huge. It's not really big. That might be nice. It might be fine. So at any point in time, I have to think through this. I'm gonna have to do this tonight.
How does it help us to have these layers?
We need to get to the thing we saw on the tank paper is not sparse.
Yeah.
Is right.
Yeah.
There's only so many combinations. What we want to do is have it simultaneously to this representation. We want to have a very sparse representation so that we can make specific predictions to layer 4. And we'll say, given this location on this particular object, I need a very sparse representation.
Yeah.
Make sense?
Yeah.
The challenge is, how do you have a sparse representation where the sparse representation path integrates? That if I told you what the sparse representation is right now, and I told you move in this direction, it deterministically tells you what the next sparse representation is.
And the grid cells would determine the next.
Well,
sparse
grid cells,
representation.
these aren't sparse. I can't,
Yeah, but they would create the sparse.
well,
representation.
whatever the path integration method would be. Okay, whatever the path integration method says, okay, we're supposed to move in this direction, right?
Yeah,
That would apply to each layer here, whether it's done through a mini column or if it's done some other way, I haven't specified it. I'm just thinking, how would I represent this? What would be a possible cellular representation that would work? So imagine now as underneath each of these, the first layer cells down, there is only two of these guys are active. These two of the equivalent ones, like
Yeah.
under this one and under this one. That's not a very good representation, right? I got two extra cells active. But let's say those two cells, all the cells in that layer try to path integrate, but only these two are active. I know, this is crazy. I'm just trying to work it through, see if it works at all. But if I had a whole bunch of layer cells, let's say I had like 15 cells deep, which is not that far. Then in each layer is only two cells active, and in each layer the same path integration occurs. Then I would solve my problem. I would have, I don't know if I solve my problem.
but no, how do you pick the two cells that are active in each
That
layer?
could be random to start with.
But if it's random, how is it path integrating?
Once I've locked in onto those cells.
So let's say you pick two random and now you're moving in a certain direction.
So that what
How do you
now
pick the
what
next
that
one?
means is that those two cells, the active cells, these would have to move. Only these cells move. Right? There are other cells here which aren't active underneath these guys, right? These guys aren't active, but when I do path integration, the active cells, they move to, the next cell over, it becomes active. The next cell over becomes active. It's not the cell moves, it's within this little thing here, the active cell changes as we move.
So that's selected by being co-located with the.
I don't know how it would work yet. I'm just trying to see even with the representation makes sense.
Okay.
We had this problem from the start. Let me just rephrase the problem. When you have a sparse SDR, you need to have a deterministic path integration mechanism that given any sparse, it has to do the right thing every time, even if you've never been there before. That's what path integration requires. Our original paper, we assumed that there were lots and lots of grid cell modules. And each grid cell module anchored independently of the others. And therefore, if each one anchored independently of the others, then in each one did path integration, then you'd always have the correct thing. Once you figure out which is the active cell in each of these, then the whole thing would move. Make sense?
Yeah.
Okay. We don't see this. We don't see what we do see. I mean, we assume like there's like 20 of these things. Maybe 20 grid cell modules. Each one has, what we do see is we see 6 grid cell modules. We don't see 20, we see 6, which is not very much. So if I were to say, there's maybe, let's say there are 20 different locations in this grid cell module, I mean, 20 different cells that tile the space or something like that, then you'd have, there'd be 20 to the 6 different ways of representing location. But it doesn't look like that. I'm sorry, I'm not able to communicate clearly about this.
Yeah, no, I understand that part.
It's even worse than that because in the tank paper, you wouldn't find 2 active. There's 6 grid cell modules. The assumption that there's a sparse. I mean, there's these are not just randomly chosen in here. In fact, it's not an assumption. He showed it that you can't randomly choose a location here, randomly choose a location here, randomly choose a location here. Sometimes these are all linked together. So if this cell is in the upper left-hand corner, this active cell will be upper left, this cell would be in the upper left-hand corner. So you don't even get all you really get is one. You have a very limited number of locations you can represent this way.
Yeah,
20, 30, whatever many cells there are in each of these things here. Or maybe it's more, I don't know, but whatever it is, it's like these are redundant, they're not building a unique representation, they're just copies of the same thing. They're all moving together. So you really can't represent much uniqueness here. So the question is, how do you get to unique SDR where path integration always provides you the next unique SDR? This method here, which we didn't invent, someone else came up with this idea. If you have a lot of grid cell modules, then it would be in each one anchored independently, then you'd have a very high representational space and path integration would work. That giving if you have a unique SDR, you would get the correct unique SDR with the motor input. This doesn't seem to exist, so I'm trying to come up with something else that might work in the same way. I suppose, now that I'm thinking about it, really what we're saying is, I could, in theory, say, well, this is like one grid cell, it's like one grid cell module that's redundant, because they're not really representing different things. So it's just like 6 for redundancy. You could argue like underneath it, there's another one, and underneath it, there's another one, and underneath it, there's another one. And so if I had 15 or 20 of these, it would be back to the thing we had in the original paper. Be like, and if you assume that this one anchored independently of this, and this one anchored independent of that, that's what we have in the original paper. But that's not what I was hearing from Tank and so on. I mean, well, I don't know. It wasn't clear. I had the impression, maybe I got down the track, since we saw some missing ones, I started imagining that this was sparser. And I started imagining this representation of sparser, that the cells underneath here were sparser than these cells. But this is close to, all it requires is that I'd have the cells here, that this module, this module, and this module, and this module all have to be anchored independently. Then it would be what we had in our original paper. But there's not a lot of evidence for this.
yeah, and in the layer idea that you just had up there, how would those get the extra information that's not in the 6 grid cell modules right now?
Up here?
Like the 15 layers underneath to have the unique SDR for each location.
All right.
If the grid cell module doesn't have enough representational capacity, would those 15 layers get the movement input additionally, or would they only base their 2 active neurons on the grid cell?
Okay, I might have made a fundamental error here. So let me just back up. Do you see the equivalent of what we had in our first paper?
Yeah.
And what we have here?
Yeah.
If it implements what we had in our first paper, that these were independently anchored, do you see why we'd have a sufficient representation?
Yeah.
Right, because we might have a choice of, let's say we have a choice of 20 different locations here, and if we had, let's say 15 of these things, you'd have 20 to the 15th different unique representations, depending how these anchored.
Yeah.
Right, so that's a big enough number. So that's the first question. Does that make sense?
Yeah.
Okay. I got down a crazy tangent, which may or may not make sense. I got down this tangent thinking like, oh, these guys aren't just like this. There was no evidence of that. There's a whole nother grid cell module underneath here, another grid cell module underneath here, and another grid cell module underneath here. That would be anchored differently, because if this is right below this, and this is only like, we're talking really small, like maybe, one cell with 10 mils between layers, like one cell body, then some of its imaging would show multiple, you'd catch some cells are just below the border and some cells just above the border, and you'd see 2 cells next to each other that look like they were active at the same time. or like two cells in the same module, like you'd see one active from this guy may be active down here, this guy's active up here, then, but you might capture and see both of them at the same time. He didn't see that. Right? It wasn't like that. He never saw like two in the same module active.
Yeah.
So then, but then we did see this idea that if you look down below this, at some point, some of these cells disappeared, which might have suggested like, oh, he was actually going down into this layer here, and he just under the border, and he caught one of these cells that was off, and he said, oh, he was measuring part from here and part from here. Like, you know, these things aren't perfect layers, or like the wiggly stuff, right? So he was capturing this part here and maybe these parts up here. So this one looks sparse. So then I'm thinking like, oh, maybe this is just a sparser version of this here. I asked him about that, and he said it might be, but he didn't know it himself. That's, I started going down that path, thinking like, oh, it doesn't look like it's like what we hoped in the beginning. So maybe something different coming. So then I was trying to make it see, do the numbers work out if I you know, this is all very speculative. Would the numbers work out if I assume that there was sort of a dense, regular grid cell array up here, and then, you know, underneath it there were multiple cells that were multiple cells underneath it, only one of those was selected, or very few, and so these would all move as a group. They wouldn't be independently anchored, but they would be sparse anyway. So I'm assuming that the grid cell mechanism, the path integration will move all of them in the same direction, as opposed to be independent and separately anchored. Clearly, the mathematically, the simplest one is assuming these are all independent grid cell modules and they all anchor differently. There wasn't much evidence for that.
Do you know if any more follow-up papers came out from that lab since then?
They probably have it. When I talked to Tank about this is very typical. I think he was, you know, like curious why I'm interested in this stuff, because it wasn't interesting to him. But that's my recollection. Not very strong, but it's like, what, you know, and you try to explain why this might be useful, and it usually falls into deaf ears. They're not thinking about sort of unique SDRs for location representations. They're trying to show, you know, to explain basic grid cells. So he said, yeah, there could be cells underneath there that, you know, I'm only, he said, maybe it's in the paper. He says, I'm only looking at a very thin layer. And I said, you know, how do you know where you are? He said, well, it's difficult to say. So, you know, we just take a layer where it looks like grid cells and then we map them out. And I think I might have asked him like, well, what if you went further down? He said, I don't know, I'll probably see the same thing. I'm not, you know, like, okay. And then when I said, why is that one not showing? He said, I don't know. And I said, could it be that you're in the layer below? And he said, I don't know, could be, you know. But could he have further papers? Yeah, he might. I don't know. You could look. Maybe look for his lab, Tank lab. I'm driving this right now purely from a math representation point of view. What would be required for our models to work?
Yeah.
Let me do the numbers here really quickly. Let's see. How many ways I can pick two? How many ways you pick 2 out of 6? Let's see. Maybe 15. You know, 15 times 15. That would work. That's the 10, yeah. Um, 15, 25. Let's 15 to 15, right? 15. What is 15 to the 15th power?
That would be approximately 4.3789 times 10 to the 17th power.
Okay.
That's what I would have said.
10 to the 17th.
Link to it.
If I assumed there were 15 cells here spaced out, like roughly about 10 microns apart. So you have a total layer, think of 150 microns, which is reasonable. That's about a sixth of the, and then you assume there were 2 out of each of these. So there was sparsity maintained throughout the columns here. You might have 2 to the 17th representations you could form. Something like that. All this is going back to the idea that we have 2 representations, a very sparse one and a not sparse one. Let's leave it at that. Is it possible? Yeah, it's possible. The numbers could kind of work out if that was true. And then you associate the less sparse one with the orientation. Here's an idea. Unless, yeah, we're doing something like this, okay.
Oh, sorry, I
It's
was
all right.
looking for more papers from the.
Okay, here's an idea. What we've just proposed here is you have a layer of grid cells that look like real grid cells. And underneath them, you have sparser versions of them where you only have the 2 out of each module active or something like that. And then we were talking about, it's kind of parallel a little bit that we were talking up here, that layer 3 was going to be more dense and layer 2 was going to be less dense. So it seemed like there's a little bit of parallelism there, perhaps. I don't know. You're looking for general mechanisms that might apply elsewhere. That's all that is. That's the only point of that is. So this represents the generic shape, something like that. And then this is the unique object locations. And then this would be and this one goes up to the what do we have here? What did we say it went up to? It was like it went to those bipolar cells. Well, this is the lower layer 3. Remember, there's a separate well, let's just take it for, let's imagine this for a moment. This would be specifying the mini columns in layer 4. So this would be like, between these two cells, you'd be somehow learning and inferring the basic shape of the object. And then between this set of cells and this set of cells, you would be learning so this bipolar connection is like, this connection here is basically learning morphology. And this set of connections here are specific objects and features.
Yeah, I really like this idea.
I'm glad you like it because it seems really cockamamie to me. Someone's trying to contact me. Seems important.
It's a very nice solution to like not relearning similar morphologies for similar, like not relearning cylinders for every cylindrical object. Essentially,
Yeah,
you just learn the specific features on that shape.
so there's a limited memory here. You can only learn so many shapes.
Yeah, but there are only so many shapes, basic shapes.
Maybe, I don't know, but there's a limited number and it's gonna be pretty limited. So, it might be, pretty, I'd be interested to sort of walk through the numbers and see like, would it handle shapes would it say all these were similar in how much generalization would exhibit it on its own because of kind of blurry bits, you know what I'm saying?
Okay.
You don't get a lot of specificity here, so it'd be kind of really blobby shapes. Seems like it would be blobby shapes. I have to think about what the representation is. But yes, for each one though, we have a very unique pattern. So does that tell me what does it solve for us here? I guess in some sense, you don't want to learn all points on an object. So that's the idea that if I'm going around the coffee cup here, I'm doing this, I'm not really learning features. I might be trying to learn features, but basically I'll be learning just morphology. And so the morphology would, there's really not much uniqueness here until I hit something that's different. So in all cases, I could learn the general morphology once, and I would make predictions on the general morphology, any object that fits in that sort of somehow. And stuff goes on. So you don't have to learn, you don't have to relearn points on common objects.
Yeah. And you remember how we talked about like having a separate feature and morphology model and kind of mix and matching them?
Do we have
putting different features on the same morphology?
Right, did we have any idea how to do that?
I don't think so, but I think this could be an idea.
Yeah, I guess that is that same thing, isn't it?
Yeah.
I forgot about that. I'm too old. That's what this is, a morphology model.
Yeah, exactly. I mean, it's a rough morphology model. We might still want to learn more detailed ones, but
there's all kinds of variations that could occur here, like there could be instead of all these cells projecting all these cells, it could be sort of a laminar projection, in which case you might have a gradient of between generic and specific. I don't know, I'm trying to imagine stuff, but anyway. Let's say there's a morphology model, which is basically based on grid cells and featured column orientation. So you basically essentially like the edges at this normal, at this angle, at this location, another location is that, another location is that.
Yeah.
I have to tweak this to get that to work well. But then there's a sparser pattern here and a sparser pattern here. This sparser pattern has to do path integration. That is, if I move, I have to move to the correct new sparse pattern. So that's that's a requirement of the model. But then I'm always able to pair unique location with any kind of unique feature.
When you say the sparse pattern needs to do path integration, do you mean it just needs to be consistent? Like when I move from A to B once, and then I move from A to B again, it will be the same two
Right,
SDRs.
it also means if I move from A to B and then from B to A, I have to go back to the same one I started with.
Yeah,
Or if
but
I move from A to B to C to D to A, I have to come back to A.
yeah, but we could, like, it doesn't have to be some predictable change in the SDR. Like we
Well,
could just associate three random SDRs with those three locations, and then
I don't, how would it know then it wouldn't be able to do that, it wouldn't be able to do path integration, because when I go to A to B to C and then I go back to A, how would it know? It has to know to go back to A. I can't learn that. I have to just know it. I have to know that I'm back in the same location.
yeah, but couldn't the grid cell modules do that part?
Right, but I'm just saying that the sparse pattern has to exhibit the same property.
Yeah, but could we just associate random SDRs with the
No,
grid cell
because
representation?
because if I associate a random one with every location, then when I go back to A, I can't predict the random one. And it can't be random. It has to be A again.
If the activity in the grid cell module is the same, wouldn't it then reactivate that
Well,
original?
this grid cell module up here is not sparse, right?
Yeah.
It's not very sparse. So this one, those cells, you know, go back to the tank paper, there were these guys, these are all go in a predictable form, you know, like you go A to B, you always come back to here, right?
Yeah.
Um,
So what I'm saying is, like, what if we just associate a random SDR with each of these possible states of the grid cell module? And whenever the grid cell module is in the same state again, it
well,
will
you can, I
reactivate.
guess you could do that. You could do that, but it can't be learned. It has to be, I don't, at some point, it has to very quickly say, I know how to do this, even though I've never, I mean, one of the beauties of grid cells is that even if you've never been to a location, it forms the right representation. What's the right representation? I mean, maybe it would work the way you said. You have to, that random association, it would have to, it might work. I don't know. Maybe it would work. I don't know. Perhaps. We can all agree, though, that it has to come back to the same unique pattern.
Yeah, I think the main issue with it, if I understand it right, would be that I think that's one of the requirements that is maybe not written yet, is that we don't want to have unions of possible locations. But so basically, we want to have locations unique to the object. So we would have different SDRs associated with the same state of the grid cell module, depending on which object we're on, if that makes sense.
Say it again.
So the grid cell module only has a certain amount of states it can be in,
Yeah,
but this should be unique to each object.
right.
So we might have the exact same state of the grid cell module, but we want a different SDR down here because we're on a different object, right?
Right. Yes. Oh, you're right. Right. I forgot about that. How do we do it unique per object? Okay. I thought, you know, like you just made a big hole in the whole theory.
Oh, I'm sorry.
No, it's good. No. There's some sense. Each one of these layers of cells has to re-anchor. Which two cells are active in those layers? Okay, so keep going. I'm getting confused, but keep going. Start again. You're talking about
Yeah,
unions, or
I wasn't even talking about the different layers right now.
Yeah.
What I was just proposing was, what if we just associate a random SDR down here with each of the possible states that the grid cell module can be in? And then in the beginning, when we don't know which object we're on, we would have multiple random SDRs active here for each of the possible objects. So that would be a union of possible locations. Don't know if we want that or not, but that would be the idea I was suggesting. And then the path integration would be done by the grid cell module. So if we go from A to B to C back to A, this would be back in the original state, has the association to the specific SDR, would reactivate that same SDR that we had active when we were at A.
Right, I'm just getting lost a little bit here. We can. We have to do 2 out of the 6 modules, two cells out of each 6 modules. We randomly choose them. Which 2 cells are active.
Yeah, I wasn't even talking about the 2
Oh,
out
okay.
of each layer. I was just saying, like, disregard the layer idea,
Mhm.
just picking a high-dimensional sparse SDR
Okay,
down here.
but all right, but I'm not sure how it works if you just pick a high-dimensional sparse SDR down there. You're trying to tell me how it would work. Right?
Yeah, maybe I'm missing some constraint. that
Well,
you're
I was
thinking
like,
about.
if I have a unique pattern here, I have to come back to that unique pattern after I moved around and come back in space.
Yeah,
How would I do that? If I just picked a random set here.
so the first time it will be a random set, but it will be associated with the state that the grid cell module is in. So then whenever the grid cell module is in that same state again, it reactivates the same SDR.
But sometimes I want to activate a different SDR, right?
If you're on a different object.
Right,
So that's where I was saying, then if we don't know yet which object we're on, we would activate a union of SDRs down here.
but why would if I knew what object I'm on,
Yeah, okay,
how do I know which one to pick here?
that's a good question, yeah.
Uh,
But we have to solve that problem anyways.
Earlier, there was
irrespective
a
of that.
suggestion that layer 3 projects down to 6. So this is the object.
Yeah, either that or the layer 4 connection.
mm. Okay, I'm running out of steam here. It's a good germ of an idea. Right? I guess my brain's not working well.
Yeah, we can take a break and,
Yeah,
yeah, we should probably also get to coding a little bit.
what time is it?
It's already 4.
4:15. So I'm not gonna stay late. I think this might be the end of the day for me.